In this video, we're going to be talking about how do we calculate volume of solids using what's called the disk method. So we're going to think about a disk as basically a circle. So what we're also talking about in this lesson is something called a solid of revolution, which you might have learned in geometry. That's basically when you take a two-dimensional shape, you continuously rotate it about an axis of revolution, and then in turn, a solid of revolution or a 3D shape is formed. So for example, when a rectangle is rotated about its height, a cylinder is formed. If you can picture in your head a revolving door, the door is a rectangle, but that whole entire structure, when it spins around, appears to be a cylinder. Now, we're not going to necessarily work with cylinders in this unit, or sometimes we're going to work with things that are not shapes at all, or a known shape anyway. So what we're going to have to do in order to find the volume is take the solid and basically slice it into these disks, in these very thin circles, and then find the area of them. And when we add up the area of all of those circles, we can calculate the volume of the solid. So again, if we think about taking a three-dimensional shape, we're going to slice it into all of these little disks. If we find the area of each disk, we can essentially calculate the solid's volume. So these are our general formulas for finding the volume of solids of revolution using disks. So the horizontal axis of revolution is basically V equals pi, definite integral from a to b, of r of x squared. We're going to say r basically represents the radius of the disk. When we're doing a vertical axis of revolution, similar to when we were finding area and volume in terms of y, that's what we're doing here. So our bounds are now y values of the region, and the radius is in terms of y, and of course dy at the end. So let's take a look at a problem here. So this one is more of a straightforward problem because we do have a triangle here, right? So if I imagine what's happening, it says we have a region R bounded by f of x equals 8 minus 2x, the x-axis and the y-axis. We're going to find the volume of the solid formed when the region is rotated about the x-axis. So if I zoom in and imagine what's basically happening here, it's continuously spinning around the x-axis, and it will start to look like a cone. Now, again, this one is an actual shape that we can identify. We know what a cone looks like, but that's not always going to be the case in these problems. So what we're going to do is we are going to use the volume formula. And again, our axis of revolution is horizontal here, since we're using the x-axis. So let me just rewrite that formula here. So it's volume equals pi, definite integral from a to b, of the radius squared dx. Now the radius, if I go back to my picture here, this is basically the center. So the radius is the distance from the upper function to the lower function. So imagine all of these little disks in here that I'm drawing. Okay, I'm drawing the radii of the disks. And I'm going to say that then when I plug in here, the radius goes from 8 minus 2x to the x-axis, which is 0 squared dx. Now, of course, we have to put bounds on our definite integral. So our bound here, our lower bound is 0. The upper bound is 4. And if we want, we could certainly rewrite this without the minus 0 in there, right? That's not going to change anything. And what I'm going to do is I've already gone ahead and typed this into my calculator to evaluate this. And I got that the volume is 268.082. All right, number 2, the shaded region on the graph is bounded by f of x equals 2 to the x equals 0, x equals 2, and y equals 0. For part A, write but do not solve an integral to express the volume of the solid formed when the shaded region is rotated about the x-axis. So this is, again, a horizontal axis of revolution. So volume is equal to pi. The definite integral is going to go from 0 to 2, right? We need x values as the bounds. Then it's going to be the upper function minus the lower function, which happens to be 0 in this case, squared dx. So again, that's basically finding the area of each of those disks. Remember, our area of a circle is pi r squared. That's essentially what we're doing here. Pi times the radius squared. And since we are going from making it rotate around the x-axis, you can imagine all of these radii in here, and you can see, okay, well, they are the distance between the upper function, 2 to the x, and the lower function, which is y equals 0. Now, for part B, they're asking us to change what we're doing here, and it says rotate it about the y-axis. So if I rotate this about the y-axis and I start making all of these discs, like you can almost imagine, I'll draw it in here just to show you what this would look like when I rotate about the y-axis. It would look something like this. And what I'm basically going to have here is I'm going to have these little radii that I'm drawing in blue, pink here, and then I'm going to have these that I'm drawing in blue. And here's what the little problem is on this one. If I look at these pink radii, they're going from the line to the curve. Whereas here, it's going from line to another line, right? It's going to the y-axis essentially. So what this means is I'm going to take this shaded region and break it into two. And I'm going to have to create two separate integrals in order to determine the volume here. So let's talk about first the one with the pink radii. So again, we're looking at my graph and we're talking about the pink radii. So it would be volume equals pi. For that section, we are going from 1 to 4. The right function is 2. The left function is the curve. So if I look at our function here, y equals 2 to the x, when I write that in logarithmic form, I get x is equal to log base 2 of y. So that is going to be my rightmost function here. Excuse me, leftmost function. Squared dy. Then I'm going to have to add in my second integral, so pi. And now these are all of my blue radii in here. So this is going from 0 to 1. The right function is 2. The left function is 0 squared dy. So in this problem, what we had to do differently on part B, we had to get everything in terms of y. But we had to also acknowledge, if I zoom back in on the graph here, that when I'm drawing these radii, like for my little pink ones here, I'm basically going from the line x equals 2 to the curve y equals 2 to the x. Whereas where I'm drawing those blue radii, I'm going from x equals 2 to x equals 0. So essentially the left function is changing in this problem. So we had to break this up into two integrals in order to write an expression that represented the volume. All right, number 3, the shaded region on the graph is bounded by f of x equals square root of x equals 0, x equals 4, and y equals 0. Find the volume of the solid formed when the region is rotated about the x-axis. So this one is going to be much more straightforward. You can almost imagine that this basically is continuing here, and this is all shaded in. This is creating our three-dimensional shape, our solid of revolution. And each of these lines represents the radius. So we are going to do everything in terms of x since we're rotating about a horizontal line. So volume equals pi, the integral from 0 to 4, upper function minus lower function squared dx. Now this one is pretty simple to actually evaluate by hand. A lot of them I've been using the calculator to help me. But if I do this by hand, you can see here that this is just going to simplify to x. So the square root of x minus 0 is square root of x. When that's squared, we just get x. So now what I'm going to do is I'm going to find the antiderivative, which is x squared over 2. And I'm going to evaluate that using our bounds. And I'm going to substitute the bounds in using the fundamental theorem of calculus. When I do that here, I'm going to get, we are going to have 16 over 2, which is 8 minus 0. And we're going to get our answer to be 8 pi. All right, for our last question here, the graph is, the region is bounded by f of x equals x cubed, x equals 0, y equals 2. we're going to find the volume of the solid when the region is rotated about y equals 2. So let's just note here that this is a horizontal line. So yes, the y-axis is vertical, but y equals 2 is a horizontal line. So that means everything's going to be in terms of x. So just as a reminder, so we don't get confused here, that would be v equals pi, the definite integral from a to b of r of x squared dx. Now, since we are doing this in terms of x, our bounds are going to be x values. I can see if I zoom in on the graph here that this is 0, 0. In order to get this point of intersection here, I'm going to be putting this in my calculator, and I'm going to find the point of intersection, which came out to be 1.259921, and then comma 2. We could have also set the functions equal to each other. X cubed is equal to 2, and found our point of intersection algebraically. All right, so now that I have that, that is my upper bound of the definite integral. And then it's going to be in this case, I'm going to do lower function minus the upper function. So I'll talk about why that is. The answer would technically come out the same the other way, but I'm going to do 2 minus x cubed squared dx. Now, here's why I'm going to reverse it in this case. So if we can imagine that basically this is being rotated about the line y equals 2, the radius is really the distance between the curve and y equals 2. Now again, if we happen to write this the other way, so in here for this note, if you happen to write it as x cubed minus 2 squared, we're going to get the same answer. That's because we're squaring it in the end. So it's almost like, as a side note, if you had 3 minus 2 squared and 2 minus 3 squared, both of them are going to come out to 1 because you're squaring it anyway and always going to get a positive. So we could technically use either one of these in here. And when I evaluated this in my calculator, I got 10.178 as the volume of the solid of revolution.